Great new and exciting things here. Spectroscopy. What's that? Is a technique used to determine structure of a compound. Maybe in Chem 1 or Chem 2 you learned that Beer's law, you could quantify a concentration using spectroscopy. Says most techniques are non-destructive, destroys little or no sample. Absorption spectroscopy measures the amount of light absorbed by a sample as a function of wavelength. So in general chemistry, if you determined a copper solution concentration by using spectroscopy, the wavelength was fixed where the compound had a maximum absorbance. It was probably in the visible spectrum of electromagnetic radiation. So electromagnetic radiation can interact with matter. Matter can emit electromagnetic radiation. Of course, you'll recall Planck's constant. E equals Planck's constant times frequency and the photoelectric effect and all that good stuff. So we're not going to do visible spectroscopy. We're going to do infrared. Laser pointer never shows up on the video. Infrared spectroscopy measures the bond vibration frequency in a molecule and is used to determine functional groups. Functional groups, that's what we get out of infrared spectroscopy. In this chapter, they throw in another technique that has nothing to do with electromagnetic radiation, and it's called mass spectrometry. So you don't want to say mass and then that word. They're two different things. What is mass spectrometry? Fragments the sample and measures the mass. Mass spectrometry can give the molecular weight of the compound and functional groups. To me, I think mass spectrometry is kind of exciting because it's kind of like maybe particle physics. What's particle physics? So when they smash atoms and look at the little pieces and determine what's in there, you can do the same thing with a molecule. If you can measure all the different masses, if it fragments into pieces, you can figure out the pieces and stick it back together. Not this chapter, but the next chapter, the whole chapter is on nuclear magnetic resonance spectroscopy. Analyzes the environment of the hydrogens in a compound. Of course, we're also going to do carbon-13 NMR. This gives clues to the alky and other functional groups present. Ultraviolet spectroscopy uses electronic transitions to determine bonding patterns. How many of you have ever had an MRI? We call that magnetic resonance imaging. It's the same thing like this, but they're doctors, they're dealing with medicine, and they decided we can't use the word nuclear. It'll put fear in the hearts of people. So the nuclear in NMR comes from protons in the nucleus of an atom changing spin states. But it's really the same experiment. You get an NMR, you go in that magnet, it makes all that noise, and they get an image of your hand, and at least that's what I had. I had my wrist done, and they can look at it. So we now have a little NMR, 60 megahertz NMR spectrometer over in the balance room. Stick a little glass tube inside a magnet, and there's a radio transmitter and receiver, and it does the experiment. And we can see what frequencies changes the spin state of the nuclei. I don't want to run too far ahead of myself on that. So here is a wavelength, and frequency is related to wavelength. How's that? Hopefully I remember. Frequency ought to be equal to the speed of light divided by wavelength, because we had from general chemistry, the energy of a photon is equal to Planck's constant times the frequency. Frequency is speed of light divided by wavelength. And of course, the wavelength can be from peak to peak, or trough to trough, or even beginning to beginning. All right, so speed of light is wavelength times frequency. Wavelength is speed of light divided by frequency. And here's this Planck's energy, Planck's constant times frequency. So I guess the point of all that is electromagnetic radiation has energy. So here's a big swath of electromagnetic radiation being the wavelength, short wavelengths, high energy, gamma rays, X-rays, UV. UV is what gives you melanoma, gives you wrinkles, cracks your dashboard. Here's where we see, and then infrared, microwave, and radio wave. So here in the radio wave regime, nuclear spin transitions between like up and down in a magnetic field. Visible, a lot of those electronic transitions. Electrons moving from n equals 4 down to n equals 2 energy levels, principal energy levels, quantum number n. So up here, these things can ionize. That means break chemical bonds, damage your DNA. That's how you get the melanoma. Where here, this doesn't do anything bad. That's why they can put you inside that magnet and irradiate you with radio frequency. We're going to focus on right below the visible region, just above the highest microwave and radar frequencies. We have these wavelengths that are usually 2.5 times 10 to the negative fourth to 25 times 10 to the negative fourth centimeters. More common units are this thing called wave numbers or reciprocal centimeters. Wave numbers are proportional to frequency and energy. So when a molecule absorbs some IR radiation and heats up, it causes bonds to vibrate. So here's a spring, maybe two masses. So there's this restoring force. If you pull it apart or if you push it together, there's some equilibrium length. And of course, if this is not at absolute zero Kelvin, there's some molecular motion going on. And if it absorbs infrared radiation, it will cause the bonds to vibrate. So here's some bond energies. So here's carbon with a hydrogen, carbon with a deuterium. Here's a carbon-carbon. And we got the weight fixed over here and we're increasing the mass over there. So the atoms are getting heavier and we see the frequency decrease with increasing atomic mass. Now of course we got this weird number here. If you put the wavelength, if you measure it in centimeters, I don't know why they did that. Normally in general chem we did nanometers just because of we're working with the visible. Centimeters, you get this reciprocal centimeters. So as it gets heavier, vibrates at a lower frequency, speed of light, lower frequency, larger wavelength. So it's a little counterintuitive. As the frequency decreases, the wave number decreases. We don't really need to concern ourselves a whole lot with that. Well, let's go back and look at this. Stronger bonds, higher frequencies. So here's a very strong bond, a higher frequency, and here's going to be what we call a stretching frequency. A nonlinear molecule with n atoms attached has 3n minus 6 fundamental vibrational modes. So water with just an oxygen and 2 hydrogens, we're going to put 3 in here and get 3 modes. And here might be the modes of vibrations. Fortunately, we don't have to do a lot of symmetry analysis to understand infrared spectroscopy and what we need to do with it. If you're a chem major, you'll do this in physical chemistry and some other chemistry classes, and you might get a book called Group Theory that's all on symmetry and spectroscopy. Fortunately, we don't have to do anything with that. No two molecules will give exactly the same infrared spectrum, except enantiomers. Fingerprint region is in between the 600 and 1400 wave numbers and is the most complex vibrational wise. And this region between 1600 and 3500 reciprocal centimeters has the most common vibrations, and we can use it to get information about specific functional groups. So for the next 20 days, I'm going to come in here and say, what does IR spectroscopy tell you? And you're going to say, what functional groups are there? Just like saying charge delocalization for all those other questions you get asked that are easily explained. Infrared spectroscopy tells us the functional groups in a molecule. Must be a big deal. It was animated and in red and bold. Functional groups. So electromagnetic radiation has a magnetic field and an electric field. We don't need to understand any of that other than a bond with a dipole moment. The bond between hydrogen and fluoride, for example, is either stretched or compressed by an electric field, depending on the direction of the field. Notice that the force on the positive charge is in the direction of the electric field, and the force on the negative charge is in the opposite direction. So here is what an infrared spectrometer might look like on the inside. Here's a toaster wire. You know, you make toast and you see that wire glow red. So it's like an incandescent bulb. It's glowing red, has a multitude of IR frequencies. And there's a way to select a certain frequency. And then there's some business here to fix drifting and noise and just make it all work out. None of it's too important. But you can put your sample in here. This reference cell is nothing. It could just be the air. But if this fluctuates in intensity, there's carbon dioxide in the air which absorbs IR frequency. Having this reference in this thing here, you can imagine it takes a difference. And so all those variables you can't control by having a reference beam. This gives more power, the rest beam gives more power, and we take a difference. Somehow we take a difference, and we get a spectrum. So these look like stalactites, and so this is absorbing IR radiation, absorbing radiation. So this is a transmittance, 100% transmittance, 0% transmittance. Where what you might have looked at in your other course, we just had absorbance versus frequency. FT stands for Fourier transform. Fourier was a mathematician, and it takes things in a time domain on the x-axis and changes it to frequency. And so all modern instruments are made this way. We still have an IR source. We have a beam splitter and some mirrors, and you put the sample in and there's a detector. It has a computer algorithm that does the Fourier transform. You go to graduate school, you might have to know more about this. You don't need to know anything about it other than you get way better spectra. Less energy is needed for the source, and it can do a scan real fast. You can take several scans and average them together. So there's this thing called the interferogram. Is said to be the time domain of a standard computer algorithm. So you put your sample in that spectrometer and it takes a snapshot. And so here is the absorbance event, and this is time, and this is absorbance. And if we take this and, well, I better not lie to you. It says wavelength. It gets changed into frequency. So this signal gets changed into something like this. Converts the time domain. Imagine that's not there. We'll look at it more in the NMR chapter. Stronger bonds absorb at higher frequencies because the bond is difficult to stretch. Conjugation lowers the frequency. So a double bond, you're going to discover it in a molecule when you do the IR experiment and you see a stalactite at this wave number. And that wave number can shift depending on what else is going on. So it says here conjugation lowers the frequency. And so you can look at these frequencies and tell something about the functional group. Carbon hydrogen stretching. So here is a hydrogen carbon stretch of an alkane. An alkane is in a functional group. Every IR spectrum is going to have a big stalactite here between 2,800 and 3,000 reciprocal centimeters. Don't get much information out of that. Here we got the double bond functional group. So this stretching here you can see in the IR spectrum, and it occurs between these wave numbers. Here's our alkyne, and this is going to show up right here. A greater percent of S character in the hybrid orbital will make the carbon-hydrogen bond stronger. The carbon-hydrogen bond of an sp carbon will be slightly weaker than that of an sp2 or an sp. So here is just a straight chain, 8 carbon chain, and here's like the fingerprint region, and then from here is the functional group. And when I look at this spectrum, I look at it and say, looks like an alkane. I don't see any functional groups. I see this thing between 28 and 3000 wave numbers, and every carbon compound has that. So here's the take-home message of this slide. In this example, the importance lies in what is not seen. I don't see an aldehyde group. I don't see a double bond. I don't see a carboxylic acid. I don't see an OH. All that is missing. The importance lies in what is not seen. The lack of, I don't see carbonyl carbon here. I don't see a broad alcohol peak here. I don't see some pointy peaks for carbon-carbon double bond or triple bond stretching where we expect to see them. All right, so here we have hexene. So we have a double bond. And the fingerprint region, it's kind of nice. We kind of ignore it. But now when I look at this, I see I see this pointy peak. I see that pointy peak. And I see this new peak. These 3 peaks are absent in that previous slide. And I'm going to show both these spectrum on the same slide here in a second. So the most important absorptions of hexene is the carbon-carbon stretch. It's pointy and it's intense, meaning it absorbs a lot. It's skinny. And this thing here. What's going on with this? I don't know. But it is a feature. But this peak and this peak tell us we got the double bond functional group. Now notice I still have the big old alkene stalactite right there and other stuff we don't need to figure out. So when you're a novice and you sit down and look at a spectrum, you're like, oh, here's this peak. It's going to tell me what the molecule is, and you try and look it up in a table, and that's kind of what we do. So here's that first one. Just a straight chain hydrocarbon. Every carbon compound has this carbon-hydrogen stretch at 2800 wave numbers. And so these peaks are missing up here. So this peak is something you look up in the stretching table and you say, oh, I got this going on. And if you have this going on, you probably have this thing going on. The 1642 is a carbon double bond stretch. So I wanted to put both these together. This, I look at it and I say, I don't see any functional groups. This one, you look at it and you say, there's this, there's that thing. Probably don't find it in the truth table, but you do find this thing. Tells you you got a double bond. Double bond is a functional group. Has known chemistry, does certain things. So here's an alkyne, and we see a sharp thing there right in the middle. The alkane doesn't have that going on. We see this stretch. Now this alkyne here is very symmetric, and I probably should have just left this whole thing out. But when it's real symmetric, the vibration doesn't cause a change in dipole, and it's invisible to IR spectroscopy. Let's look at oxygen-hydrogen stretching and nitrogen-hydrogen stretching. Both these occur over on the left, but they look different. And this is one of the easiest things to detect in an IR spectrum. It's broad with a rounded tip. Secondary amines, there's just one hydrogen. It's broad with only one sharp spike. Here's a primary amine. We got 2 hydrogens. It's broad with 2 sharp spikes. If we have a tertiary amine, we don't see that signal. Should make sense. Don't see that. So here is butanol. So here's the thing every hydrocarbon has. Doesn't tell us a thing. We kind of ignore this side. We look from here on and say, what functional groups do you see? So here's this broad, intense peak up here. That tells us hydrogen-oxygen stretching. Has to be an alcohol. The IR spectrum of alcohols will show a broad, intense oxygen-hydrogen stretching absorption centered around 3,300. 31, 32, 33, 34, 35. Right there it is. The broad shape is due to the diverse nature of the hydrogen bonding interactions of alcohol molecules. Diisopropamine. So this is a secondary amine. That means there's just one hydrogen. So here's this broad thing. It's not as intense as an alcohol. It has this little spike. And you're tempted to look at that one and say it has two. Must be a primary amine and not a secondary. Well, hopefully I'll have an example where you see both the spikes for a primary amine. The IR spectrum of amine shows a broad nitrogen-hydrogen stretching absorption centered around about the same spot. Here, 35, 34, 33, right at 3,300 wave numbers. Diisopropylamine only has one hydrogen, so it only have one spike in the spectrum. Ketones, aldehydes, and acids. So carbonyl carbon, we see in all these ketones, aldehydes, and acids and esters. The carbonyl bond here of a simple ketone, aldehydes and carboxylic acids, absorbs around 1,700 reciprocal centimeters. Usually the carbonyl is the strongest IR signal in the spectrum. It's going to be very intense. Carboxylic acids also have this OH. Aldehydes are going to have this carbon-hydrogen signal around 27 and 28, real close to the carbon-hydrogen of an alkane. So ketone here, 2-heptone. 7-carbon chain and the carbonyl carbons on the second carbon in. And here's the strongest peak in the spectrum. Look, it's like the most absorbing 1718. Pretty close to 1710, close enough. We'll see how sometimes it can shift back and forth and what might cause that. So here's an aldehyde. Here's our carbonyl carbon, pretty close to 1710. Looks like it's this way just a little bit. But here's this stretch that's pretty close to our standard business here. It's really hard to see, but when you see this little feature here and this, tells you aldehyde. So this spectrum here, we see carbonyl carbon, and we see this broad stretch there. Now notice the alcohol was centered around 33. So we don't want to think this is an alcohol. It shifted. It says this OH absorbs broadly at 2,500 to 3,500, and both peaks need to be present to identify the compound as a carboxylic acid. So we see carbonyl carbon in an alcohol. Normally this comes like this. Any questions?